Our next speaker is Colin and Crowley. You can read the title.
Yeah. Cool. So thank you. Very broadly, I'm interested in hyperplane arrangements. And in particular, like many people in this special year, I'm interested in the interactions between their geometry and their combinatorics. One instance of this interaction, Connor told us about in yesterday's session. He talked about the top-heavy conjecture. And he mentioned in particular these varieties that show up in Crowley. These were first studied by Federico and Adam Booker. And the proof of the conjecture was by June and Otan. So these varieties and their combinatorics is one story. Another place where you can observe this interaction is in the cohomology of the complement of an arrangement of complex hyperplanes. This is the well-studied Orlik-Solomon algebra. And in 2001, Terao introduced what I'll call a commutative version of it, which is known as the Orlik-Terao Algebra. So this is sort of sketchy, but I'll just say it's a commutative version of the homology, the complement, if you are defined over C. Okay, but it's some algebra. And there is a connection to the first story. Yet a third place where these two things will interact are these zonotopal algebras. These come up in the study of box splines, and in particular, I want to talk about the internal zonotopal algebra, which was introduced by Olga Holtz and Amos Rahn in 2011. More work on these algebras was done by Federico and Alexander Postnikov, who studied a broader class. So the work that I want to tell you about today touches all three of these stories, and the connection that it brings between the first two is different than the usual one. Okay, so very generally, that's what I'm going to say. But for this talk, I want to focus on a particular example, which is already pretty interesting. And that's the hyperplane arrangement associated to the type A root system, which I'll call the braid arrangement. So the main example for today is the braid arrangement. All right, nice. So by definition, this is the arrangement of hyperplanes Hij, where the I and j coordinate coincide, living in the ambient space, R to the n plus 1, modulo the span of the Alban's vector. Here's the picture for n equals 2. Okay. And the associated Orlik-Terao algebra is defined to be, well, I'll write it OT. It is the algebra generated by the reciprocals of the linear forms xi minus xj. I'll think of it as graded, where every generator has degree 1, And Terao showed that this algebra has a presentation which looks very much like the defining presentation of the Orlik-Solomon algebra. However, it is for a polynomial ring as opposed to an exterior algebra. There's also an Artinian reduction called the reduced Orlik-Terao algebra, which I will write OT bar. And this is the quotient by the following linear system parameters. So I'll take a sum of some generators, I not equal j, where I is something in my index. And by Artinian, I mean that this OT bar has finite dimension as a complex vector space. Okay, and the symmetry group Sn plus 1 acts on the braid arrangement, and so it acts on both of these algebras by permuting the labels. So in this case, it will be interesting to ask what is the structure of this OT bar as a graded Sn plus 1 representation. Okay, so that's one thing. Now let me tell you a little bit about internal zonotopal algebra. Again, just in this special case. So in general, this is defined as the quotient of a polynomial ring by certain powers of some linear forms. But by a very nice coincidence, the internal zonotopal algebra, which I'll write IZ, of the dual of the braid arrangement. So there is this Gale duality for hyperplane arrangements, which I won't mention because I don't need it, but in any case, a related arrangement. This is isomorphic to the even degree cohomology of the space of configurations of n distinct labeled points R3. This cohomology ring. And this has an Sn action by permuting these labels, but it also, you can define an Sn plus 1 action in this sort of clever way. So there is a homeomorphism between configurations of n distinct labeled points in R3 and configurations of n plus 1 distinct labeled points in group SU2 of special unitary 2x2 matrices modulo simultaneous translation. Okay, and why are these two things homeomorphic? Well, I can use the group action to make sure that the last point in my configuration is the identity. And then what will remain is a configuration of n distinct labeled points in SU2 minus the identity, which is R3. And now the Sn plus 1 action acts here by permuting the labels. So there is this clever Sn plus 1 action that you can put on the cohomology. And a theorem of Roberto Pagaria in 2022, which was conjectured 6 years earlier by Daniel Mosley, Nick Proudfoot, and Ben Young, states that as graded Sn plus 1 representations, these two are the same. So Pagaria proved this by finding a very clever way of computing the Frobenius characteristic on both sides. You get the same symmetric function, so they must be the same representation. I should also mention that Mosley, Proudfoot, and Young proved that these are the same when you restrict to Sn, and that's why they made this conjecture for Sn plus 1. Okay, so some remarks on this statement. The first one is I didn't really present it like this, but there are nice presentations for both these algebras. So this can be a very explicit algebra problem when you write it like that. However, two, as algebras, these two things are not the same. So you cannot solve this problem by proving that two presentations are secretly the same, because they aren't. They are genuinely different algebras, but they're the same as representations, which is a little strange. And something even more strange is that these are both functorial, but the variance is opposite. So if I have an injection from a smaller set of labels to this set of labels, it induces a forwards map on the ICs backwards map on the OTs. Okay, so not only is the ring structure different, but the variance is different. And so from this point of view, it would maybe be more natural to say that these two algebras are dual to each other as vector spaces, rather than naturally isomorphic. And so here's our theorem statement. So for a hyperplane arrangement A, find over the complex numbers, we construct natural isomorphisms. So one is between, so you take this internal zonotopal algebra, whatever it is, of the dual arrangement, and you take the vector space dual. This is isomorphic to the reduced Orlik-Terao algebra. So that's one. And this does recover Pagaria's result, because a natural isomorphism will be respected by whatever group action, and any representation is non-canonically isomorphic to its dual. And two, sort of interestingly, we can also connect it to this one. So we show that this internal zonotopal algebra, up to multiplying it by a one-dimensional vector space that I won't really specify, I'll just write character. So times some character, if you're looking at representations, is isomorphic to a group of syzygies in this work of Dila and Booker. Or if you like, another thing this is isomorphic to is the cohomology of a certain line bundle on the same thing. Okay. So here are these three things that turned out to be naturally isomorphic, and sort of an interesting special case was done for SN. That's the surprising coincidence. The main idea in the proof comes from this work of Nick Proudfoot and Tom Braden, where they show that this OT coincides with the intersection cohomology of a certain of an affine hypertoric variety. So they developed this machinery of minimal extension sheaves on posets, and they show that this thing satisfies such rigid conditions that anything else which satisfies those conditions must be isomorphic to it. And that's sort of the approach we take. We show that both of these things satisfy a certain sort of rigidity. Okay, And that's all, so thank you very much.
Are either of these true integrally?
Yeah, I think. Let me actually get back to you on that one. Yeah, I don't know off the top of my head.
So I don't think I understand the definition of OT bar. What is that quotient bar?
Oh yeah, so these are my generators.
Okay, so that's just a symmetric algebra, is that right? Abstractly.
No.
Okay, so I'm not, maybe I don't understand even what OT is. What is OT?
Yeah. So these are some rational functions, and they have some relations between them if you sort of play around with them. So like in this 1, 2, 3 example, there will be a relation between 1 over x1 minus x2, 1 over x2 minus x3, and 1 over x1 minus x3.
Okay.
So there, even starting from here, there are some relations.
And then you're quotienting by for each one, yeah, each value of I, you take that sum.
Yes, okay, that's right.
You define what this star is.
Yeah. So one way to talk about a hyperplane arrangement is to, I can use the defining equations to like define an injection. So here it would be from c to the n minus 1 to like c to the n choose 2, number of equations and dimension of the ambient space, as n. And then what I do is I take the orthogonal complement in the dual coordinate vector space. This is another subspace, and you get another arrangement.
Sorry, both sides of your isomorphism in one are commutative rings, but the isomorphism involves a dual. Is it possible to see the other structure directly on the other side?
We're interested in this, but we don't know how. Yeah, the co-ring structure on either one is not obvious to us. Yeah. Yes.
Can this Orlik-Terao algebra define purely for matroids, or does it really depend on the arrangement?
It really depends on the arrangement. It's not defined purely for matroids. And I believe the same is true for the sonotopal algebra. So this is really a story about arrangements.
So, we're off to coffee and cookies.